Materials supplied by Microsoft Corporation may be used for internal review, analysis, or research only. Any editing, reproduction, publication, rebroadcast, public showing, internet, or public display is forbidden and may violate copyright law.
I think we can start. So good morning. Thanks for coming here. Good morning to those who watch us online. Today we have Ivan Dokmanic from Audio-Visual Communications Laboratory in EPFL in Switzerland with his advisor, Professor Martin Wetterli. And today he is going to present the results of his 3-month-long internship in Microsoft Research here. Without further ado, Ivan, you have the floor.
Okay. Thanks, Ivan, for the introduction. So I'm Ivan. And I'm going to tell you.
I'm Ivan, he's Ivan.
That's right. So I'm going to tell you a bit about what I was doing in the last 12 weeks, actually. So let me start with first things first. Just a small thanks or a big thanks to everyone that sort of helped me out with various technical difficulties while I was doing my project. So the audio group, or Mark, I couldn't find a high resolution photo. Jens and Ivan, right? And also I'd like to thank the hardware team. So Jason Goldstein and Tom Blank, specifically Jason, I'm just mentioning you, who helped me a lot with building, and debugging the hardware. Okay, so let's start with a short overview. I'm basically gonna start with trying to motivate why you'd use ultrasound for something that's typically done with light, and is done very well with light, and go through some basic principles really fast of ultrasonic imaging. Then I'm going to talk about our hardware design and beamforming, how to get directivity, some calibration issues, some annoying things that happened, and so on. And then I'm going to move to algorithms. I'm going to describe the naive algorithm. So the first thing that you try to do, imitate the way you do it with light, and then why this doesn't work really well, and the things that we sort of tried out, and some of the things that turned out to work much better, some things that we propose. Specifically for increasing the resolution and for increasing the frame rate, so for obtaining it's like a usable frame rate, okay? And then I'm going to go over some experimental results and suggest things that could be done in the future to get even better results. Okay. So, let's start with why ultrasound. Depth imaging, is typically done by light, either by using sort of, the disparity between two images, two photos of the same scene, or by using lasers, for example, in Kinect and in LiDAR. So this is good, and this works fine. But for example, if you want to use cameras, you actually need the camera. You need a device that does it, which can be quite large, quite expensive, can use a lot of power. With lasers, there's potential always to use a lot of power, and these are all very fast signals. Light has a very high frequency, so you have to take special care in the design in order to design the circuits that are good for RF frequencies and so on, right? So what are the ways that ultrasound can sort of provide something else? Some of the advantages are the following, right? First, the frequency range. The frequency of the ultrasonic sound that we use is 40 kilohertz, and 40 kilohertz is fairly low in comparison with the frequency of light, right? So this means that you can design very simple hardware. You don't have to pay special attention to PCB design, to RF design, and so on. So the design is very simple. On the other hand, the propagation of the sound is fairly slow in comparison with light, right? So this means that your wavelength is not going to be too large, which is good, because for imaging, you don't want your wavelength to be large. So this is somehow a fortunate coincidence, right? Other good thing is power consumption. So I snipped here 2 images from the data sheet of the transducer that we're using, and you can see here that at frequencies of interest, the impedance of our transducer is something like 500, say 500 ohms. And we want to drive it to get maybe 100 dB of SPL of maybe 105, so we want to drive it to maybe 5 volts RMS, which results in 10 milliwatts of power consumption if you use it full duty cycle, right? But we don't use it full duty cycle. We use it only a part of the time when we emit pulses. So do your math. I mean, we can really go low in power consumption. Sensors are cheap. They're quite available off the shelf. The ones that we have are fairly cheap ones. And in some ways, it's complementary to light. So light might fail, if you have, for example, a thin piece of fabric in front of you, or if the space is filled with smoke, or if there's a lot of mirrors. It could be complementary in some regards, right? So of course, there's a lot of challenges with ultrasound, perhaps much more than advantages when you look at it for the first time. So first challenge is that the frequency is still low. So there's no way, to get the level of detail ultimately that you would get with light, because the wavelength is, for example, of this ultrasound that we use, a bit less than 1 centimeter. Another issue is directivity. If you have lasers, well, lasers are quite directive by themselves, right? There's no mention of trying to make them more directive. But with sound sources are typically not so directive. And so, we need to find a way to sort of imitate what we have with lasers with sound, okay? And another issue is slow propagation. That's a very annoying one. So if you want to imitate light, so if you want to raster scan the scene using ultrasound, something maybe 3 meters away, for a pulse of sound to travel there and back, it takes maybe 15 milliseconds, which would amount to maybe 60 points, 60 pixels that you can scan in a scene. Or if you want more pixels, you'll have a really lousy frame rate. This is not good, right? This is completely unacceptable. So we need to deal with that. And the most annoying thing probably is the specularity of sound reflections. So sound always reflects specularly. Very small part of this reflection is a diffuse reflection, which means essentially that if I'm standing here and I'm shooting directly to the wall, I'm going to hear a strong reflection, right? So if I have a source of sound here and the receiver there, then a strong reflection is going to happen somewhere there. But if I'm trying to see what's happening there with the source and receiver standing here, I'm out of luck, essentially, because the sound will not reflect here. There is a small diffuse component, but it's completely impossible to see it with what we currently have. So we also need to somehow deal with this. Okay. Another challenge is, of course, attenuation of ultrasound in air. Sound always gets attenuated when it travels through air. There is this, for point sources, we have 1/r law, just because if you put some energy in a point source, then it travels, and this energy is spread over larger and larger spheres. So if you're listening in a certain point on this sphere, you hear sound that's with lower intensity. But ultrasound gets attenuated in air because of the compression and expansion of air, much more so than the ordinary sound. In fact, above frequencies of around 100 kilohertz, you get attenuation of more than 3 decibels per meter, which is quite substantial. So for something 2-3 meters away, you would be attenuated to something like 20 decibels, okay, which is quite a lot. So with all these challenges, a completely legitimate question is why bother at all? Why try to do it? And we have a good example in nature of these beasts that can actually do quite well with ultrasound. So how we hope that the limit is far away. We still don't do as good as they do. These are quite fascinating little creatures, and they use frequencies that are mostly are ultrasonic. So all the way up to 200 kilohertz, and they have fascinating resolving ability. For example, the big brown bat can detect spheres of roughly 2 centimeters across at 5 meters away. Okay, and perhaps the more fascinating thing is that they can resolve detail, which is 1/5 of the wavelength that they're using. So beyond the diffraction limit. Okay, using some heavy spectral processing, and their great brain. We're not quite there yet, but sort of we can hope for it, right, in the future. Okay, so let me go quickly over some related uses of ultrasound. And ultrasound is mostly used. So the vast majority of ultrasonic applications are in biomedical imaging, and for a good reason, right? So not so much ultrasound was actually used in air, and a typical image that you see in biomedical applications is an image like this one, okay? And this is called a B-mode scan. So what is a B-mode scan? How do you obtain a B-mode scan? There's the simplest possible way of obtaining an ultrasonic image is by just inserting sound, so emitting sound into the body, and then recording reflections as a function of time, and plotting them as a function of time. If you do this in 2 dimensions and encode the amplitude of the reflection as the intensity of the pixel, you get an image like this, okay? So in body, you can do that, because always some part of the sound will get retransmitted, okay? So something will reflect from here, but some sound will go on, okay? Then it will reflect further. And the medium is like this random scattering medium. So every point of your tissue acts like a small scatterer and reflects some sound back. Okay, so in air, perhaps, in the late 70s, that's one of the first uses. Polaroid was using ultrasonic sensors as range sensors in their cameras. Okay, and then there were people like Lindström in the early 80s that tried to image the spine deformation. Okay, they were trying to use ultrasound in air to image spine deformation. So they were scanning mechanically an ultrasonic device along the spine. Okay, and they were obtaining images like this one. Then in the early 90s, they were trying to use ultrasound to measure the skin contour. So it's slightly higher frequencies. And these sensors were always very close to you. Okay, so this is not our scenario where we want to image something that's further apart. Okay, further away. So more closer to what we're doing, we have some more recent developments by Moebus and Zubir, for example, from 2007, where they use 400 microphones in a synthetic aperture to try to image objects that are, a meter or 2 meters away from the imaging device. And we also have some attempts to build aids for visually impaired people. For example, these guys use 64 electric microphones to image the scene. And these guys here also use ultrasound in air, but they use different. I'll come back to this later a bit. They use different kind of transducers, different than us. Something very small, very, very, very efficient, and something that's probably the future. So that's why I'm mentioning it here. And what I'm showing here are 2 images from the paper by Moebus and Zubir. So they were trying to image, here they were imaging a PVC pole. I'm not sure exactly at what distance, but I think it was 5 centimeters across, okay, with 400 microphones. So this is the image that they obtain, okay? And here they're trying to image a cubical object, also the same distance. So you understand that specularity is a big problem, right? I mean, you see now what I was talking about when I was talking about challenges of ultrasound. There is no way to get a reflection from this part of the pole here, because this doesn't reflect back to the device. So keep these images in mind for later. Okay, so let's talk a bit about hardware and beamforming and everything we have to do with this. So first thing first thing that I had to do is I had to choose the proper transducers and proper sensors. And this was quite a challenge because you sort of need to understand what will play correctly with the hardware that we have here, moto units, how to interface these things to a PC, and so on. And so very common design of the transducers is piezoelectric. Okay, so just a piece of crystal that vibrates when you apply AC voltage across it. And these are some typical designs. So this is a closed one. If you have to expose it to the elements, this is the one that actually we use. The device is here. The whole thing is here. I can send it around later. And then you have these things all the way. So these are really small ones. These are really big ones. They spend something like hundreds of watts. Okay. And I found this black one on this guy here. I found on eBay, and the seller lists a couple of intended functions. He says 1, medical treatment, 2, beauty device, 3, heal algae. Okay, so there you go. I mean, yeah. Here you have another example. This thing here is 350 watts. Okay, and it goes up to 35 kilohertz. I'm just showing it to understand that there's a huge diversity of these things. And the guy whose webpage I took this from says the sweeping ultrasound can cause certain adverse effects like paranoia, severe headaches, disorientation, nausea, cranial pain, upset stomach, or just plain irritating discomfort. Great for animal control. so yeah. I mean, a lot of interesting things out there, right? So this is our device. And once again, thanks, Jason, for helping immensely with this thing. Okay, we're sort of debugging this infinitely, and still it has a lot of problems, but we sort of did our best, right? And so let me talk a bit about microphones. Okay, so I explained what kind of transducers, what kind of sources we can have. These piezoelectric devices, they can also act in the opposite direction. When the crystal vibrates, they generate AC voltage, so you can use them as microphones. But we decided to do a different thing. So we're using here MEMS microphones typically intended for use in cell phones. Okay? And these microphones are typically intended to go up to maybe 10 kilohertz, but it turns out that they also hear 40 kilohertz. Their polar diagram should be omnidirectional, which at 40 kilohertz, and with our design, apparently it's not. I'll talk about it later. This is kind of a challenging point. But the nice thing about this particular model by Knowles is that it has a preamplified differential output. So even if I drive it to the preamplifiers, I'll show on the next slide, actually I could use this directly to drive Motu's line inputs. This is very convenient, and it has a differential output. Okay, and these are the transducers that I was talking about. We interface everything to a PC using, first to Motu using DB25 snakes and so on. This is the battery to power the microphones, and this thing uses a separate power supply because we need to drive it to maybe 10 volts RMS. So we can't use a battery for it. We could do it. Okay, so this is the overall design of our system, right? We have here the microphone array and the speaker array. Microphones go to microphone preamps and then to Motu unit, and everything is driven by MATLAB, from a PC using the firewire is actually USB. A cool thing, as I'm saying, is that you could actually drive these guys directly to Motu. This is something that we learned later, but this is just in case we wanted to preamplify them a bit. Okay, so let me talk a bit about beamforming. For those of you who perhaps don't know what beamforming is, which is none. So, we have to find a way to direct sound to certain directions and also to listen directionally. So it turns out that if you have more than one microphone or more than one loudspeaker, even if this microphone is, for example, omnidirectional, with more than one, you can achieve so that the overall characteristic, the overall directivity of the system is selective. So by properly playing with the signals that you record from these microphones. So we can use this to create a beam of sound or to listen in a beam of sound and try to steer this beam electronically, which is another cool thing because you can do it electronically by changing the way you play with these signals and to scan the scene. Okay, so there's many ways to do beamforming, but somehow two opposing extremes are something we call minimum variance distortionless response. Beamformer, it's not important what it really is, and delay and sum. And they're different in the following way. MVDR is great if your system is perfectly calibrated, and then it gives you the best possible beam. Okay? But if your calibration is imperfect, then actually it could perform worse than a very simple beamformer, which is delay and sum, and which turns out to be the most robust to manufacturing tolerances. So we sort of lean towards the delay and sum beamformer because, well, unfortunately, we don't have excellent calibration of our device, even if we wanted to have it. We tried. So this is a polar diagram of a three-element microphone, just to understand how these beams look like. Okay. So if we're, for example, listening, microphone array, right? So if we're listening towards the direction of 0 degrees, we get sound intensity of 1. And if we're listening, for example, to 30 degrees, then we get less than a third, but still quite substantial, right? It's still a lot of sound coming from this direction. Okay, something cool that we can do using this beamforming theory is we can think about how to properly design the geometry of our microphone and loudspeaker arrays, because obviously not all geometries are equally good, right? Some geometries will provide us with better beams and some with worse beams. We need to find a way to measure this, and a reasonable way to measure it is using something called the directivity index, which is just, if B here is the directivity pattern, directivity index just says, what is the ratio of the directivity towards the direction that I want to be looking at with respect to the average directivity in all directions. And this is a completely reasonable measure. And so what we're trying to do, what I was doing is, I took a couple of candidate geometries, so a cross geometry, a square geometry, and something like a circular geometry, and I was varying for each of them the spacing, the pitch between microphones, and I was evaluating the directivity index for the corresponding geometry. And I was trying to find the best one. It turns out that for microphone array, somehow, the best overall geometry was this square one, and the spacing between the microphones that we use is 6.5 millimeters, which is slightly more than lambda a half, than half of the wavelength. Okay, so this is the finalized geometry. For loudspeakers, for buzzers, for sources, unfortunately, we couldn't optimize it properly, and the reason is the physical size of the thing is just too large, right? So we have a mechanical reason. And we can not to be able to put it as close as we would like to. So their pitch is 11 millimeters, which is the smallest mechanically allowed pitch. Okay, and what you can see here is that we angle the transducers a bit out. We tilt them out. Again, this 20 degrees here is not an accident. It's an optimized number, somehow the best one. And the reason is that the transducers themselves are a bit directional. So in order to cover a wider field of view, it's a good idea to just tilt them a bit out. It turns out that the beams in extreme directions will be better if you do so. Okay, so this is just a simulated beam from our microphone array. This is just to understand that even if you want to have a point here, a pixel, we don't have it, unfortunately. So this is what you would get if you would be looking at the beam from the front and just flatten it. So if you have one scatterer, a point scatterer, then instead of seeing a point scatterer, you see something like this. Okay, so this is the meaning of this image. If you remember how it looks like, it's 3 microphones, essentially laterally, and 3 microphones vertically. So with a 3 microphone array in some direction, you can't use much. We have 8. But if you want to extrapolate the performance you have in a horizontal plane, you need to square the number of microphones, okay? So for example, the performance that you get with 8 microphones horizontally, you'd get with 64 microphones in the whole space, okay? Okay, so let's go on, right? Calibration. Calibration is important. Of course it's important. We want to have perfectly calibrated things. For example, here we have the frequency response of our transducers, actually of some other transducers, but all of them are roughly the same. So you see that at 40 kilohertz, they're the most efficient, okay? And as you move away from 40 kilohertz, they are less and less efficient. So we want to equalize this. We want to, because we assume in beamforming that they have a flat response, right? So we need to push the frequencies away from 40 kilohertz. We need to push them up, okay? So things to calibrate are phase, amplitude, and polar response. So we should also measure the directivity patterns of these small devices if we want to do the proper complete job. So the way I did this is in the anechoic chamber here. And, I was sort of pointing, I have a laser here. Let me show you this. So I stuck a laser here, and I was pointing this laser at the microphone to sort of ensure that I'm really looking at the main response axis of these arrays. I was doing it many times. Unfortunately, I was only able to properly calibrate the loudspeaker array. There is an issue of repeatability, and I couldn't figure out why, but especially with microphone arrays, their directivity pattern is not at all omnidirectional. So small tilts of these things resulted in completely different gains. So we had to use some sort of overall good gain. Okay, now enough of that. So let me just show you the actual correction filters, how they look like for the loudspeaker arrays, just to show you that they make sense, that they look like something that we expected. So on the left-hand side, you see the correction to the amplitudes that we have to make. So you see at 40 kilohertz, they're very efficient, so we don't need to do anything. Away from 40 kilohertz, we have to amplify them, okay? And you see that phases are fairly reasonable. Here you also see another thing. You see that 2 of the transducers are very silent for whatever reason. So we really didn't have time to debug this piece of hardware anymore. So we just said, okay, we're going to amplify them digitally. So you see these 2 transducers, we have to push much harder than the other ones in order to perform the same. Okay, so to highlight the importance of proper calibration, I'll just show you an example of a loudspeaker beam with and without calibration. And just this morning, I realized what I'm showing here is actually the microphone beam with loudspeaker correction filters. The message is the same, don't worry. So on the left, you have the calibrated beam, which I already had shown you. And on the right, you have an uncalibrated beam. Perhaps this image shows it better, right? So the uncalibrated beam looks weird. And even if it's more beautiful than the one on the left-hand side, we actually want to have the one on the left-hand side, right? And you can see actually these side lobes are most likely the microphones that we have to push harder, okay? Have to do something with them. Okay, so now that I'm done sort of with hardware, let's go to algorithms. Okay, okay. First, I want to explain how in general you create ultrasonic images, right? What do you do? So I already was talking a bit about beam mode imaging, where you sort of emit sound and then plot reflection intensity across time, along the time axis. So in every mode of ultrasonic images, you emit some pulse, okay? And then you measure some parameters of the returned pulse. And depending on which parameters of the returned pulse you measure, you get different sort of modes of imaging. So beam mode I already discussed, okay? So in air, when you use ultrasound, beam mode imaging makes limited sense because nothing is getting retransmitted. If I get a reflection from that wall, I should not hope to get the reflection from the wall in another room, the way it works in your body, okay? So it makes much more sense to do something that we call intensity image. So just find the returned pulse from each direction and plot its intensity against angle. So this will be somehow an intensity image. And then in depth imaging, we're not interested in the amplitude of the pulse. We're actually interested in the timing of the pulse, on some temporal property of the pulse. So when the pulse comes back. Okay, that's how we create depth images. Okay, and so these are somehow different approaches. I'm going to quickly go over them and some problems, and then, you know, I'm going to tell you how we solve them. So naive approach is just a raster scan. So to do exactly what a LiDAR does, for example, a raster scan, pixel by pixel, find the time of flight in this direction, find the time of flight in this direction, plot the times of flights, and you get your image, right? So the problem with this is you have seen the beam, and in reality it's worse. So this is not going to work very well, right? I'm not going to be getting time of flight from this direction. I'm actually going to be getting something that's coming from the side lobe most of the time. Okay, I'm going to come back to this later. So we sort of propose some techniques for deconvolution. I explain how this is different from deconvolving an intensity image, and you know how we can deal with this. So then I'll propose another method based on sound source localization. So how we can couple sound source localization with beamforming to get slightly better images, to get actually usable depth, quote unquote, images. And I'll tell you how to improve the frame rate. So frame rate is one of the most annoying issues. So I'll explain you how to improve the frame rate from the naive approach, where the frame rate is completely unacceptable, to something that's completely acceptable, like 30 frames per second, while exploiting the whole, you know, every transducer that you actually have. Okay, so before moving on, I'll just briefly go over the choice of the pulse that we have. This is a topic in its own. Bats use chirps. We don't use chirps. Bats are much smarter, so they use chirps. We use something that's quite peaky, and it's like a filtered Dirac pulse, okay? So it's just a complete passband pulse between 38 kilohertz and 42 kilohertz that we use. I could have plotted the autocorrelation of this thing so that you understand how our image, when we try to estimate the time delay looks like, but the autocorrelation of this thing is actually this thing. So it was not necessary, right? Because you see how the spectrum looks like. So this is just a filtered Dirac, and here's the formula. It's a difference of two things. Okay, so this pulse turned out to be very good for detecting reflections when they come back, but perhaps, you know, you'd want to take some more time to actually design the perfect pulse. Okay, so let me explain a bit about deconvolution and why we have to think of different ways to do deconvolution than conventionally is done in ultrasonic imaging. So typically deconvolution is done for intensity images. And so now imagine that you have, you know, that wall over there is a source of noise, is a noise generator. And different parts of this wall generate different amounts of noise. And so imagine that the wall is created by very small pixels of noise, something smallest that you can detect. Well, you know, then I direct my beamformer towards a certain part of that wall, and I'm not able to listen to individual pixels. What I'll be listening to when I direct the beamformer in some direction, I'll be listening to a weighted sum of all these pixels. I was trying to represent this here mildly successfully. So you get the weighted sum of this intensity across the beam shape, okay? So this is actually convolution, some convolution, either, you know, spatially variant or spatially invariant with the beam shape, and this is a linear equation. So the convolution here amounts to inverting a linear system. Then you can talk about conditioning, you can talk about do you really know the beam shape and things like that, but basically it's inverting a linear system. That's the convolution in intensity images, right? For us, we sort of, these small beams are supposed to represent these individual pixels. So what is the image creation model that we have in depth imaging? Well, you know, imagine that you have, that each small reflector here, each pixel emits something when you know, reflects a part of your sound back. And this sound, the reflected sound, I call x of theta, so for different directions, theta and t. So this is a function of time. Then again, this gets convolved with the beam shape because you're not listening just to a particular pixel, you're actually listening to a weighted sum of pixels. So there's a convolution with beam shape. Then what we do is we cross-correlate this with our pulse template in order to find peaks, right? So, you know, I just wrote it as a convolution with some pulse template u, and then we actually create the pixel by finding the maximum, by finding the largest peak, okay? So this is the time, Okay, the time of the largest peak. So this is our depth, right? So obviously this is not a linear model because there's a maximization inside. Okay, we cannot write this out as a matrix multiplication of some true depth image with some beam shape. Our measurements are not linear. Okay, and so there's no hope to just do very simple deconvolution, as is the case in the linear, in the intensity images. Hope this is partially clear.
Why not the earliest time?
The earliest time
Instead of the maximum.
Oh, because the signal, because you will not actually get, so what if you have a continuous surface? So no discrete distances in your, then you'll get some sort of a smeared pulse, right? So it's like, that's a good idea. And actually I'm using this idea in something else with source localization. But the thing is that you're not really getting the correct, if you have a very wide beam, you'll get some weighted sum of these pulses that will overlap in time, okay? So it's the question of how to disentangle these pulses, Okay. Did this answer your question?
Because
You'll not get discrete, most of the time you will not get discrete separated pulses. They will be overlapping if the surface is continuous. So I'm somehow trying to give the complete creation model. Okay, and well, for what it is, first part of the image creation model in this case is definitely convolution. So if you at certain time, the output of the beamformer at a certain time is actually some combination of the outputs of these perfect beamformers, or the reflections that you would be getting from the smallest pixels. So by X here, I denote the smallest pixels, and you get actually for every time you get some combination of them. Partial I here represents all the pixels that contribute to the ith beam. That's just a short annotation for that. So this again is some kind of a convolution. It is a convolution, right? It's a two-dimensional convolution, and we can write it out as a matrix multiplication with some Toeplitz-like matrix A here. So since this is correct for every time instant, we can sample the left-hand side and the right-hand side, and we obtain a matrix equation like this one here. Now observe that this matrix equation has some vertical structure determined by the convolution. So vertically, things on the left are some convolutions of things on the right with the beam. But what we don't exploit here quite yet is the fact that this matrix X has horizontal structure, okay? And this horizontal structure is the structure of the pulse. So let me explain this. If you emit a pulse and you have just one reflector in your scene, 1 point reflecting, what you'll be getting back is the same pulse again, at least in shape. Forget now filtering, but roughly what will come back is the same waveform, attenuated and delayed, right? So this means that really every row of X here has to be an attenuated and delayed copy of the pulse, okay? Of the pulse that we emitted. So this means that we can enforce this in our modeling by representing, sorry, this should be D here, D. By representing X as a multiplication of a selection matrix, of a sort of delay selection matrix, and the pulse dictionary. So D here is a pulse dictionary. Every row of D is a different shift of our pulse, and then matrix B just acts so as to select the proper shift for each individual pixel. These ones are just representing non-zeros. So B is obviously very sparse, and we know exactly how sparse it should be. Ideally, it should be having only one non-zero per row, because each infinitesimal pixel only gives one single reflection. And so the way to obtain the true B, which is then the representation of our depth image, is by trying to minimize the vectorized, it's like compressed sensing-like, trying to minimize the vectorized one norm of our B matrix, thus trying to minimize the number of non-zeros, while ensuring that what it yields is not too far away from what we measured. Okay, and then you can have some non-negativity constraints. So one thing that you could try doing is you could try to eliminate the dictionary from this matrix by multiplying everything from the right by the pseudo-inverse of the dictionary. This will generally perform worse because the conditioning of this dictionary is not very good, and so this will amplify the noise and you'll get a worse equation. But an advantage of this thing is that it's now separable. Here B is in the middle of the two matrices. Here B is sort of alone, and you can solve this column by column. So it has potential to work faster. So this is just briefly some simulation results. So for this, I only have simulation results. The reason is we haven't been able to really measure so far the exact shape of the beam, and this requires it. Not perfectly, but at least, to some extent. So this is some artificial depth map that I created, low resolution, because this thing is, for now, slow. And this is the mask that I was using. So I convolve this thing with this mask, and I generate temporal signals using some pulse that I generated, okay? And I add a lot of noise to this pulse. And then I run the algorithm, and this is what you get. So you can get the convolution performance like this one, even with sort of 10 dB SNRs. So with a lot of noise, which is much more than you would be getting in practice from ultrasonic images. So this is just sort of to show you that this thing really works. Works surprisingly good, but unfortunately slow, right? And for real problem sizes, it's still too slow for anything real time. Okay, so next problem is, of course, these side lobes, and the thing that I was talking about before. So say you think you're looking there, okay, but your side lobe is looking towards that wall, and you're thinking getting a reflection from there. But if a reflection from there is 1,000 times weaker, and your side lobe is only 100 times weaker in this direction, you'll be hearing this wall, okay? And it's pictorial here. So in practice, we don't have 1:100 ratio between the main lobe and the side lobes. So this essentially means that you don't know what you're listening to because of the side lobes. There may be nothing there, but you'll get a reflection from here. Okay. Hope this is, the illustration helps to understand. Okay, so our proposed solution is to couple this with source localization and to do it in the following way. So what I'll do is I'll listen to that direction, and I'll beamform in order to get sort of as directional thing as I can in this direction. Then I'll find peaks in the beamformed signal, and I will go back. I'll show this again. I'll go back to the raw signals recorded by microphones, and then I'll feed them into the source localization algorithm. And I'll try to find out where these reflections are really coming from, okay? And if where these reflections are really coming from doesn't agree with where I'm looking at, I will not put the pixel there. Okay, so this is a block diagram of the whole system. I have microphone signals here. I feed them into the beamformer, but also into this generalization of music that I implemented, which is just a generalization of, it's like both for azimuth and elevation. Music is a very well-known source localization algorithm. So, for example, I concentrate on some frame. Okay, this is one frame. This here highlighted in red is one frame, so it's one direction. And I feed this into the beamformer. This is the output of the beamformer, okay? And in this output, I find peaks. Here I find one peak. But actually, I find several peaks every time. Okay, I find, for example, the largest 3 peaks. Okay. Now what I do is I zoom in to this peak and go back to raw signals, and I feed these raw signals into the source localizer. Okay? And I found out, and then I try to see if the direction that this reflection is coming from agrees with where I think I'm looking at. Okay, and I do this for many peaks inside every beamformed signal. This is an output of the source localizer. This is just sort of the score for each direction, okay, for each possible direction. And you can see that, for example, in this particular frame, there were 2 sources active. For example, I could have been standing like this and imaging myself, and I got a reflection from this hand and this hand together. Okay, this makes sense because they arrive at the same time, but they're obviously arriving from different directions. Okay. What I really do in practice is for every direction, I make a list of distances. So I'm not just saying, okay, this is the distance in this direction. I actually make a list of distances. So I have a large list of distances for every candidate distances for every direction, and in the end, I pick the smallest one, because the smallest distance makes somehow physical sense, and it turns out to give good results. Okay, these are just for fun, some possible outputs, some possible score maps of this sound source localization algorithm. Remember, we don't have so many microphones, right? We have 8 microphones for the full azimuth and full elevation. So that's why this is not so peaky. But you can see that sometimes we have a clear one source active. Sometimes we have multiple sources in the same frame, which completely makes sense, right? So, okay, I'll show you results for this later. So now I'll move to the next problem, and the next problem is frame rate. So what people do with frame rate is, because frame rate suffers because if you want to do raster scanning, so we want to point the beam at every possible location, then it's just too slow, Sound travels too slow, as I said, and it's going to take too much time. So what people typically do is they say, okay, we can do microphone beamforming in the computer. We can do it offline. So we'll just use one source, just splash everything with sound, and record it with microphones, with a lot of microphones, and then do microphone beamforming offline. But the limit on the frame rate is then quite high because, well, you just need to send one chirp, tick, and then only do the receive beamforming. So now there is benefit in using multiple sources of sound also. I give here an example by Moibus and Zubir, who do a great job in imaging with 400 microphones, but they use this argument, right? They say, okay, we're not going to do transmit beamforming because that's too slow. Okay, so we just use one source of sound. So what we propose to solve this problem is something really simple. It's just the basic properties of LTI systems. I'm going to tell you a bit about why probably people don't do it too much. So let's go over what microphones hear. So this is the signal that microphones hear. So let's say that SI here is the signal emitted by the ith source, okay, and the HIJ is the channel from the ith source to the jth microphone. Then for all the microphones, for all the sources, the jth microphone just hears the sum of these convolutions. Okay, that's very simple. So for us, every signal emitted by a certain source is a filtered version of some template pulse that we're emitting. So we can write out this SI as some WI, which is the beamforming filter for this particular beam and this particular microphone, and U is the template pulse that we're using. Okay, so we can rewrite this in the frequency domain just as multiplication. So now look at this, right? I mean, it has two distinct parts. First part is something that we know, for sure. We know the beamforming filter because we designed them. Okay, so this is something that we have in our device stored, and there is a part that we have to measure, that we have to put physically into space and then measure, and it's this part here. So it's how ith source excites jth microphone. Okay, but now if we knew this part here, which I denote with R superscripted I down there, if we knew this red part, we could actually create this sum offline. You agree? There's no reason why we wouldn't be able to create this sum offline. Okay, so what we can do actually is we can learn the red parts easily by firing every transducer individually and recording ours, and then just do the transmit beamforming offline. You agree with me? It's simple linearity and commutativity. There's nothing special to it. But it allows us to only do 8 chirps if you have eight sources, and recreate every beam computationally. And instead of having a frame rate of 1/12 of a frame per second, we can actually have 30 frames per second for a certain resolution. So just why probably people, I mean, of course people know this, but why probably they don't use it too much is that, well, 2 reasons. First, for lasers, there's no thinking about it. Lasers are themselves very directional, and you do raster scanning. In loudspeaker beamforming, usually people want to listen to sound, okay? So they reproduce sound for people to listen to. And then you can't use this. You can't have a loudspeaker array of 20 loudspeakers and then play each one of them individually and then say to someone, okay, now do the beamforming mentally in your head. This is not good. You want to create a sound picture, okay? But here we don't care. We're creating an image. It doesn't have anything to do with listening to actual sound. So we can do this. Okay, this is just the block diagram. So what we do is we play a delayed version of the pulse through every loudspeaker, filtered by corresponding correction filters, store whatever is recorded by microphones. In our case, this is 64 signals, and then we create everything from these 64 signals. Okay. This actually came out from a discussion with Ine, who suggested this for deconvolution. This can actually also be used for deconvolution. I'll talk about it in future work. So these are some results. Brace yourself. And then some future work that I think could be done in order to really, really improve what I'm having. So this is the experimental setup at some time of the night in the atrium of our building here. Cleaning ladies were not very happy that I was preventing them from coming here. I was doing the experiment in the atrium because with the current design, the beam is still too wide, and the reverberation doesn't do me well when I'm in a room. So when I have a lot of reflecting objects in the room, the images are worse. So that's why I went to the atrium in order to have a smaller number of reflections. I mean, the reflections are coming much later. Okay, so results. I was imaging myself, okay? And because this thing, I didn't mention something. Somehow the underlining of all of this is skeletal tracking, okay? What we're trying to do with this is we're trying to see whether we can design, it's an exploratory project, whether we can design a skeletal tracker using ultrasound instead of light, okay? And so I was standing like this in the atrium with my arms folded, next to my body, and this is the image that you get. So first thing, remember what some people get with 400 microphones, and I mean, they do a really good job, right? But you understand that this is actually not bad. No, it's not bad because you can actually see that there is a body here. Beyond all questions of how much my body reflects ultrasound, beyond the fact that not every reflection here is specular, but you can actually see something. Okay, so now this is what I'm showing you. This is an intensity image, which means that in every direction you just calculate the intensity. What we want to have are depth images. So naive way to create a depth image is to just, as I said, point the beam there and measure the time delay. Okay, and I said this is not going to work because of the side lobes. And indeed, this is the depth image that you get with this naive approach. I'm showing this to you just for the drama, right? So you see everything is at 2 meters. Almost everything, because every time I'm standing there, right, and every time some part of the beam, some part of the side lobes will catch my body and will create a reflection. So I'll think that everything is at 2 meters. Right? After applying the sound source localizer to this, we get a much more reasonable thing. So you see that now only the pixels that I can trust are sort of shown, and these pixels are at correct distances and they're sort of aligned with my body. Of course, this can be improved further with further work, but this is pretty large improvement from this. Okay, so now let's see a more interesting thing. Okay, and this is kind of cool. So what happens if I spread my arms? Okay, so arms are quite small, whatever, and they're not very good reflectors and specularity, whatnot. So if I spread my arms, you can actually see it in the intensity image, which is kind of I have to say, like maybe 4 weeks ago, I lost hope for this, right? But now I'm sort of really happy that I got this image. This means that you can see where the arms are, okay? So imagine having much more microphones. Imagine having better algorithms. You could probably, do very well. So you can actually see where the arms are. Again, just for comparison, this is with arms folded, and this is with arms spread, okay? So you see arms here and here. Depth image, again, naive approach. Everything is, at around 2 meters. Not very good. If you apply sound source localization now, and this is good, we get something like this. So you get this alien-like creature with some imagination is me in depth spectrum, but this actually shows something, some body and some arms spread. So it's much better than this. And it's actually pretty good because the distances are correct and the arms are in correct positions. Reasons why this works is that on the body you have many kinks, parts, small detail that actually does reflect sound sort of in different directions. So you can hope to find something around here that will reflect sound back to your device. Okay, and what I'm showing here is the same thing, but with this fast frame, sort of single shot acquisition with linearity used. Again, with my arms folded. This was a different experiment, so this is not the correct photo. I should have put in a different photo from that experiment, but there was no people in the atrium that could take a photo of me at that time, so I had to give up. But you see that the image is somewhat worse. I would expect the image to be exactly the same as the other one. Unfortunately, for some reasons that I haven't been able to debug yet, the image is slightly worse, but still, it's sort of correct, right? And again, everything is I was standing a bit closer, at a bit less than 2 meters in the naive approach, where I sort of recreate these beams. If I apply sound source localization, then you sort of see the head, which is a strong reflector, and you see arms. This requires further work. Requires, it's not quite clear to me why this didn't work as expected, but in theory it should. So this is probably just a bug. Okay, so these were the results, and I'll go over some of the conclusions. So what do I have to do? I had to design this hardware with a lot of help from Jason. I had to, this involved a lot of things, like what to pick, how to interface it to a PC, definitely how to design the geometry. And so I explored various image creation algorithms. And the images that we have, they have 3-degree angular resolution. You could create finer images, but with current beam shape, it doesn't make much sense, right? I mean, they wouldn't have much physical meaning unless you were able to properly deconvolve them. So 3-degree angular resolution is somehow a qualitative good number for good number of pixels. Okay, so I proposed some convex optimization based and sound source localization based algorithms to improve the depth images, to improve the actual depth estimation. And so one of the major problems, speed of sound. I proposed the solution. An experiment, it still needs some work, but definitely the solution is to use multiple transducers, but to use these simple properties of LTI systems that I can do things offline, even in transmitting. Okay, and so this takes us from 1/12 of a frame per second for the naive approach to 30 frames per second for 8 transducers for this approach with transmit beamforming online. And the good thing about this, the great thing about this, is that this doesn't scale, right? The time, if you fire only 8 transducers and get more sophisticated algorithms, you'll still need exactly 1/30th of a second to acquire the frame, because you only need to fire 8 transducers. So it doesn't scale. See what I'm trying to say? So you can have very sophisticated algorithms after this, but the image acquiring is going to be very, very fast. Okay, so the limit is sky. Major advantage of this thing is low power consumption. Again, things operating lasers, they use a lot of power. Okay, it does depend on the number of pixels, but typically they use a lot of power. So in this regard, our prototype uses 3 watts, but this is a lot. And this is because of the nature of the operational amplifiers that we're using. The quiescent currents are quite high. But if you do the design specifically for these transducers, you could achieve something like, for the 8 transducers at once, like 1 watt in pulse. Okay? And perhaps 10% of duty cycle. We're not using them all the time. This results in maybe 100 milliwatts of the power consumption. Then if you go back here and you do a single shot acquisition when only 1 transducer is active at the time, you could actually, you could perhaps divide this by 5. So get something like 20 milliwatts, which is really, which is a huge difference if you compare it with what you need for lasers. Microphones virtually don't need any power. Okay, and so the question somehow, that I forgot, I didn't highlight enough in the beginning of the talk is, it's like ultrasound for skeletal tracking. Well, I think that probably the answer is yes. If you use high frequency and you play with algorithms, you have proper calibration, I'm pretty sure that you can extract enough meaningful features about positions of limbs in order to create a skeletal tracker. And so let me go just quickly through some possible future directions. So definitely there is value in B mode or intensity images. So perhaps we could use these images to maybe detect connected regions or something like that, right? And then use them to enhance the depth images. Okay, so there would be value in combining the 2 information to build like a reasonable skeletal tracker. Then for the actual skeletal tracking, well, what is the information that we use? The information that we use is 64 signals that we recorded. Okay, so perhaps the important features are times and intensities in every temporal bin of these 64 signals. That's what matters. So what you could do is you could divide these 64 signals into bins, compute the average intensity over every bin, and feed these as features for the training of the skeletal tracker, right? You see what I'm trying to say? So you could not create the depth image at all. You could completely bypass the depth image and just get the skeletal tracking from these features, which directly encode actually the positions of objects in the scene. Okay, we can formulate the deconvolution that I was proposing directly in the signal domain, never creating beams. Okay, so we can also formulate this deconvolution starting from 8 by 8 signals that we have. Similarly, as for the other thing, and of course, the most mundane idea that we have is increase the number of microphones. Okay, so nowadays the guys Prizibila, one of the papers that I've shown in one of the first slides, they use something called capacitive micro-machined transducers. And these things you can fit, it's like, for example, they fit 37 microphones on a PCB 6.5 by 6.5 millimeters. It's quite fascinating. Problem currently is that they work at slightly higher frequencies, so their range is limited. But I think in very foreseeable future, this is going to be the technology of choice for ultrasonic imaging in air. Okay, so just as an example, like what could you do? What could we do if we had 64 microphones? Okay, so this would be the beam shape, right? And this is the beam shape that we have currently. Okay, so obviously virtually no side lobes. It's still quite I mean, it's still not a point, right? It's still some piece of a beam, but it's much better than what we currently have. So many of the problems will be mitigated with having more microphones. Okay, well, that's roughly everything that I had to say. Thanks for listening. If you have any questions, please go ahead.
Actually, to have some questions. You're trying to just take one picture using the ultrasound and then turn it into skeletons, right?
For example, yeah, but I mean, you'd do it consecutively.
Yeah. Then how many frames did you use to create those?
Oh, these are all single frame. Single frames, yeah.
Do you think it'll get better if you use multiple frames and just...
I'd say yes. I mean, no is obviously wrong answer, right? So it can't get worse. So it would get better because it have some smoothing over time. So you could probably use this also to get higher resolution.
Then just occurred to me, you're using a single pulse, right? Single frequency pulse, right? Like on the...
We use a band from 38 kilohertz to 42.
Yes, but do you think it's possible to shift that, like make the beam a little smaller and you shift it into multiple frames? So for instance, on the first frame you shoot from 38 kilohertz to 39 kilohertz. On the second frame you shoot 39 to 40, something like that. And
it's like OFDM kind of
a chirp-like signal, but it's not exactly a chirp, but it's like a beam, but like that.
Yeah, definitely. I mean, we were thinking about things like that. So one thing that you could do for sure is, use multiple frequencies. Not like 38, 39, but try to use 40 kilohertz and maybe 80 kilohertz, or 40 and 73. I don't know. And then this could be really useful to remove, for example, coherent speckle or some effects that are the artifact of the actual frequency that you're using. So the thing that you're suggesting would be great also, for example, for improving the frame rate further. In the following sense, if you could use this kind of OFDM, idea, if you could use separate bands, you could actually emit, one pulse, so one beam in one part of the spectrum, other beam in other part of the spectrum, and other beam in the third part of the spectrum, all at the same time. Okay, so that's a good idea, but it requires a lot more design, and you need a slightly more wideband. So had a lot of trouble with this thing, with repeatability of these transducers. Okay, sometimes they don't work as expected, so you need a more reliable source of ultrasound that you can. And that's more wideband, okay? Because these things are very narrow band. It's 40 kilohertz and a bit aside. So we need to push things a lot, right? Maybe you'd like to have something that has a much wider bandwidth, and these things exist.
More questions? Yeah?
Two questions actually. First, in terms of what exploit stuff, so you're most interested in a dynamic. So interested most in what's moving. So can you exploit? So can you exploit the difference from frame to frame? So you issue that as one frame, and then say, "Oh, I don't even care what's here." And when I do the next, like, well, what's different now? And these are the parts, and then try to figure out which parts of that are different. That's the part that's kissing.
Definitely, yeah. I think that's a good idea. It's actually, now that you're saying this kind of reminds me of maybe someone is familiar with phase vocoder, so or something like this. You're trying to determine a real frequency. You have an FFT of something, and you're trying to determine the real frequency, right? So the way to do it is to take two consecutive frames and see the phase change and interpolate the frequency, right? So and then you're not limited to the bin anymore. You sort of can get the real frequency. So yeah, I think this could be really useful, because maybe also intensity image could be used for that, right? Because some intensities would slightly go down, some intensity would slightly go up. So you could probably interpolate, play on this to get a much better image.
And the second question is, like, when you're doing about like this sparsity decomposition of that matrix of getting the basis functions and so on. So one of your hypotheses was there's only one signal coming from a certain pixel. But due to multipath, that's actually not true, right?
No, but it's if you really have said that you really have a really narrow beam, that you can really listen to this particular pixel, then what would have to happen is that you have a multipath component that comes from the exact same direction, and this is very unlikely to happen. Well, because it's probability 0. So in the limit case where you have infinitesimal pixel, if you're reselling exactly to this direction, then to have also a multipath component coming from exactly this direction is probability 0. A lot of random things should align in order to have a couple of reflections and then suddenly a reflection again from there. Right?
The probability isn't it the same that something comes back from that?
It is, but say that it's like infinitesimal pixels for me are. Okay. Perhaps I didn't understand your question, and yeah, I see what you're saying. Okay. So, for example, if I have a mirror, how will I know that it's a mirror, that it's not something over there? That's a good question, and the answer is there's without further information, there's no way to tell it, right? So if you're just using this information, there's no way to tell. You should be able to estimate the positions of such big reflectors. One way to do it is, probably be too slow. But since this is all modeled by image sources, actually, one way to do it would be to try to combine pairs of pixels to get a third pixel. Pairs of how to say this? Okay, so this reflection from that wall will also have a corresponding object there, right? So they have a clear geometrical relationship. So the object that creates the reflection will also be hopefully inside the scene. Okay, so since this object, you have seen this object and you have seen its reflection, but maybe you know that there is a wall here. There is it's like this geometrical relationship between the reflection and the real object, and you can detect the reflection, okay, by exploiting this image source relationships. You can say, okay, this guy is actually a reflection of this guy. I'll just prune it out. That would work, but it would probably be too slow because you need to combine pairs of objects in the scene. But that's one idea on how to remove this thing.
More questions?
The problem of the side lobes picking up reflections where you don't know if they're in the side lobe or in the main lobe. Did you consider treating it as a filter design problem whereby at the expense of increasing the size of the main lobes, you could suppress the side lobes and reduce the probability of a reflection falling to the side lobe, but at the same time reducing the resolution of the design to the wider main lobe?
Yeah, actually I have it. I mean, that was initially one of the ideas to sort of design the beam pattern. Then later we didn't really do it. Reasons are that we hoped that the side lobes are not going to be so loud, and then later I sort of just forgot about it. Then the main lobe is still quite wide, and if we did it like that, then it would be even wider, considerably wider probably. So it would be beneficial, but okay. So the main problem with side lobes is with specular reflection, right? So I'm trying to get something from there, and say that I'm hoping, I don't know why, but I'm hoping for a small diffuse reflection from something over there. Okay, and here I'm getting a strong reflection. So this diffuse reflection will be, for example, 1,000 times weaker than a strong specular reflection from there. Okay, and I doubt that, especially with 8 microphones, you can create a beamformer that will suppress everything but the main lobe more than 1,000 times. I mean, I'm sure that you can't. So you see what I'm saying? It's like the problem is that if there is a strong reflector in the scene, and even if you're shooting just a bit of sound or listening just slightly to this direction, you'll hear everything coming from this strong reflector. It's like that one reflector in the scene has a reflectivity that's 1,000 times stronger than the other things in the scene. So maybe some fabric and then a piece of wood. I'm just talking gibberish, but then everything would seem to be coming from this piece of wood. I'm not sure if I'm clear, but
maybe if you were to practically deploy to say in a living room where there are reflectors that you expect always to be there, you always expect to have tables, walls, and ceilings and things. Could you have a calibration procedure that determined where they're likely to be, make sure that the nulls of the side lobes are pointing in the directions where you expect reflectors?
Yeah, I didn't think of that, and this seems like a really practical and good idea. Yeah, why not? So yeah, you just sort of move out of the way, calibrate, and then go and use it. Yeah, this is actually good, especially with more microphones and more transistors. You could certainly play on that. Yeah.
In some senses, that's a bit like NVDR in the sense that if you walk out, then your noise is your unwanted signal, which might be you're reflecting.
Mm-hmm.
You first try to minimize that,
And you can
in
do
such
the
a way that,
adaptation of what?
yeah, such that when you actually come back in, then the only thing that's in the room is the wanted signal, and that's going to be you.
Yeah, I like this idea. Yeah, I think this could be really good.
More questions?
Can you increase the microphones without increasing the number of transducers?
Of course, that would be something that you would do. So there is benefit in having more than one transducer, and the benefit is the following: you can sort of partially isolate regions of space, which is good for sound source localization. I can elaborate on that later. But definitely, what you would do is you would not increase the number of transducers too much, but you would increase a lot the number of microphones.
More questions? Okay, let's give a thanks to our speaker today.